I'm going to be recording these for, because we have online students. So a little lesson about how that works. These go on a YouTube channel. Microphones in the ceiling over here, not super sensitive. Over here, super duper sensitive. So if you're sitting over here and you think you're going to have a whispered conversation, no one's ever going to know, everyone's going to know. Okay? Just letting you know, over here, super sensitive. So, molecules bouncing around a chamber, what causes the gas pressure?
Force down.
It's a force. So it's the molecules hitting the walls of the chamber and transferring energy. So the act of the molecules themselves hitting the walls of the chamber are causing the pressure. Gases usually come in the form of homogeneous mixtures. How did we do on vocabulary last semester? So what do we think about? Okay, I want to get this out of the way because I always end up saying this in class, and there's always someone who giggles. You're probably at some point going to hear me talking about HOMO and LUMO electrons, okay? And I say the HOMO electrons, and there's always someone who giggles, and I'm like, yeah, it's an acronym. That means highest occupied molecular orbital. Those are usually what we call your frontier orbitals, and they're the ones primarily responsible for chemical reactions. So HOMO, highest occupied molecular orbital. LUMO is your lowest unoccupied molecular orbital. So these are just terms you got to get used to. Now, in this case, we have the two prefixes, homo and hetero. What language do these come from?
Latin.
Greek. I think it's Greek. Double check it, just make sure. Also, keep in mind, just because a person with a PhD says something doesn't mean it's always right. So the prefix homo, what does it mean? Same, hetero. Different. So homogeneous mixture, think of a homogeneous mixture like the air in this room. What is it? What is a homogeneous mixture?
Mixture of what everything is. It's like the same thing.
So let's think about it this way. What compounds are in the air? Nitrogen, oxygen, carbon dioxide, hydrogen. A lot of different compounds in the air you breathe. Can you see any of them? That's heterogeneous. The mixture is in such a way that you cannot tell the difference between the distinct parts. It all looks like the same thing. Heterogeneous, just think of ice and drink. You can see the ice, you can see the liquid. You can see a definite boundary between the two species. That's heterogeneous. When we're talking about pressure, there's a number of units we could use. So here's a small table of conversion factors. I like to compare everything to atmospheres because we're going to be talking about, for example, what if I told you, let's ask this. Is standard temperature and pressure and standard conditions the same thing? No, they're not. Now, both of them have 1 atmosphere of pressure. However, standard temperature and pressure is 0 Celsius, whereas standard conditions is room temperature or 25 Celsius. So that's a little trick. When you're looking at exams, read what they put there. If they put standard conditions, you go, oh, 0 Celsius, 1 atmosphere. That's standard conditions. So I always use the 1 atmosphere because that exists in both standards. So you see that 1 atmosphere is worth 760 millimeters of mercury, which comes from old apparatus. It's like the word octopuses or octopi. Which one is it? I don't know. Is it apparatuses or? Well, good thing we're not Englishers in here. That's why I also don't grade your grammar, because mine's awful. So you have these old things like a barometer. They used to put mercury in them until people realized, oh, there's a certain sect of our society we can't trust to not lick the mercury. So you have to change the whole thing because people are getting sick. But the reason it was called millimeters of mercury is you'd have this setup and you'd have mercury exposed to the atmosphere. the atmospheric pressure would push on it, force mercury up the column, and you could tell what the atmospheric pressure was. You have another type of pressure called torr. And you see that it's equivalent to millimeters of mercury. Then you have pascals, which, if this is important to know for standardized exams, SI units. The pascal is the SI unit of pressure. So if they're ever like use SI units, you're like, I got to use pascals. 101,325 pascals is 1 atmosphere. And then we have one there called bar. We will do some problems that have PSI. What is PSI? Pounds per square inch. I don't like them because they're in English units. I never got the idea of the foot because I don't like it because it was the freaking king's foot. You get a new king, you get a new foot. So it's weird, you know, but we still use it, so whatever. Okay, something else we do in class is we do exercises. Some I'll work through with you. Some you're going to get in groups and you're going to work on together. So make sure you're sitting next to people you like to talk to. Or if you don't like to talk to them, fake it. Okay, so here we have 2200 PSI. Express this in atmospheres, megapascals, and torrs. So that's something else you're going to have to get used to, is your metric prefixes. And you have a nice table here from tera to nano, pico. One they never give you, though, it's never on these tables. You ever notice how these tables skip 10 to the negative 10th? You know why? What is 10 to the negative 10th? It's a scale that we usually measure chemical bonds in. Well, what would the unit be called at 10 to the negative 10th meters? What's that? That's the angstrom. I would get used to that unit as well. That's 10 to the negative 10th meters. Now, let's look at part A. And so these are going to be short, but this is an idea of how I like problems worked out. So I use the grid method. I don't care if you use a grid or if you use like you're multiplying together fractions. The whole point is we want to set this up in a way we're canceling out units until we get to where we want. So I'm going to start at the 2200 PSI. Now, if you've seen this, you know that everything across the vertical bars is multiply. Everything across the horizontal bars divide. So essentially, you're multiplying up the top, multiplying up the bottom, dividing the two. And we do this because we know, like, let's say you divide x over x. That's 1. So this way, we're trying to set this up to divide out the units we don't want. So you see here we have 14.7 PSI per 1 atmosphere. And you see that the PSI divides out the PSI, and we end up with the unit we want. So you end up with about 150 atmospheres. Okay. The next one, megapascals. Well, I could go all the way back to the PSI, but I already have the atmospheres, and I can take atmospheres to pascals. So let's just start there. $150 atmospheres. Okay, so then, I go up here and I see that 1 atmosphere is 101,325 pascals. I want to cancel out the atmospheres. Okay. And then how do I go from pascals to megapascals? Well, let's do an actual conversion. So look at the table here. Mega is your capital N. So I see that there are, what is that, 10 to the 6th pascals.
in 1 megapascal. Now you could flip this if you get another table, because you could say 1 Pascal is 1 times 10 to the negative 6 megapascals. You could do it the other way. But I think it's easier just to use what's on the table. That way you're not, you don't get confused. So then you see that pascals divides out, atmospheres divides out. And when you multiply this, you should end up with about 15.2 megapascals. Now, this has a number with scientific notation in it. What kind of calculators are we dealing with this semester? What kind of calculators do y'all have? Well, like, brain. Yes. Does anyone use, so you can actually type out 1 times 10 to the 6th on here, and it might work. But that is not how the firmware in is designed. Yes. Yeah, you see, there's a button on your TIs that has the EE. You type 1.0, hit that EE button, and then type 6. That EE is times 10 to the, you type in the, whatever the exponent is, okay? That is the most reliable way to have a calculator get your scientific notations correct. And with your calculators, use parentheses like your life depends on it. Do not trust your calculator's order of operations. You put everything in parentheses, I just don't trust it. Okay, so then from here, what was the third one? In Tor. Okay, well. When you're doing your homework, I don't care if you cross things out. I'm just showing you that that those units divide out. But like if you were doing this problem, I would want to see you set it up like this so I can track each step that you're taking. So what do we have here? What conversion factor do I want to use? 150 pascals, not pascals, 150 atmospheres. Mm-hmm, 760 torr. And again, the unit I want to go away needs to go on the bottom. Atmospheres divides out, and you end up with that. So we'll do it both ways. Now, you're going to have to use your judgment when doing assignments. I would accept 114,000, but sometimes these numbers are going to start to get so big that it's going to be ridiculous to write them all out. So we translate this into does everyone remember how to do their scientific notation translation? Good. I usually think once they get beyond the thousands, it's nice to just start going ahead and translating them. Otherwise, you're just going to be writing big old numbers. Now, that's one type of exercise we'll do in class. Another one is I'm going to be putting stuff in like this that will help train you for standardized exams. So talk amongst yourselves and see if you can figure out the answer to this one. Work in a group. Definitions can be fun. I also found out for some reason students really don't like true-false questions, so I don't ask them anymore. It didn't matter how I wrote it my first year, they always thought it was a trick question. Just, it's like, it's ridiculous because believe it or not, I am neurodivergent, so I don't do trick questions. I'm actually painfully literal. So it's, I will warn you, sometimes I don't know the difference between inside thoughts and outside thoughts, but that's a whole nother thing. So what do we think it is? It is D. So let's think about that. Mass an object exerts when at rest. Well, you can look at that a number of ways. It's like the kilograms you possess in your mass, or it could be your weight, which is your gravitational force. Well, that's not pressure. Measured in newtons. No, why? What is newtons measure? Force. It's the wrong unit. Defined as the number of moles of a substance divided by the mass of the substance. That's close to a unit we are going to learn. Does anyone know what that is? Moles per kilogram? That's grams per mole. Moles per kilogram. We're going to learn about a unit called molality. And moles per kilogram will be molality. Measured in grams. Well, no, again, that's just mass. So it has to be D. Now, getting groups again, here's a harder standardized exam question. What kind of tool could you use to solve this? Which of the following is the highest pressure? Now, if you were running out of time and you were just going to guess, which one would you pick? Which would be letter what? Yeah, see, that's absolutely wrong. That's how these standardized exams get you.
PSI.
It is the PSI. How do you know?
7.1 atmosphere
Mhm.
and 11.7 is like 80
Mhm.
or something, and then
So-
with 0.5 is less than.
Now, I'll tell you the technique I use. I just take these and translate them all to the same unit, see which one's biggest. And so it's like, if I looked at this and I say, well, what I have, oh, I'm going to translate everything to atmospheres. So let's start with 437 millimeters of mercury. Well, I know that there's 760 of those per atmosphere. That's going to give me about 0.575 atmospheres. So if I'm just looking at A and B, I now know it's no longer A. Okay, well, let's look at the next one. Let's look at 11.7 atmospheres. You notice how in this problem I didn't tell you the conversion between PSI and atmospheres? It's because I've already told you that once. So if you're looking for a conversion that I didn't put down, and it's not in the textbook, I probably told you somewhere. So go find it. Again, if you have your computer out, go to Google and type in 11.7 atmospheres in PSI. Google's real good at translating. You should get a, yep. So now C is the largest one. Now that will help with homework, but keep in mind, you can't use Google on exams. So you're still going to want to know how to do these conversions. And let's look at the pascals. Well, I know, and the reason this one is it's the biggest number, so your eye is drawn there. But remember, you're going to have to divide it by 101,325, which is going to give you 0.652. So it's the second largest, but it's not the largest. That's the highest pressure. So a lot of these, especially as we get into the chapters that are more geared towards chemistry 2, you're going to see exercises like this. And questions like this are things you're going to see on your exams. It helps you develop tools that you can then go into the final exam with, that you're like, okay, if I see this is how I'm going to attack that problem. You don't have much time, but we're going to start getting into gas laws.
So the first gas law we're looking at is called Boyle's law. And that is for and these, and I have these highlighted in purple because these are the keys to this. For any constant temperature, the pressure times the volume is a constant. So what this tells us then, I like that one. It's actually a really accurate way to learn those organic structures. So if we rearrange this, our volume, and K is just a standing constant. We don't know what it is. Also remember these slides are going to be on Canvas. And pay attention, anything that you see in like the reddish pink, that is your theorem. I highlight those so that you can pick them out. Now I'm going to use a symbol that a lot of you probably have not seen before. So first off, let's look at this. You see the graph there of the volume versus 1 over P? This is why scientists will put things in these different formats, because you want to know what that constant is at all pressure and volume equal. What you need is the slope of that line, because you see how your K times P would be mx plus B if your B, if your B is your y-intercept, if it crosses the y-axis at 0. You see that? So your K is your slope. So it's the same format as y equals mx plus b. And you're going to see me do this a lot. That's just, that's a mathematics shorthand for this becomes 0. Now, we're going to have to start getting used to the idea of this. For Boyle's law, it's not the best drawing of it. What did I write there? Not alpha. Let me try. It's not a letter. It's a logic symbol. Have you ever seen this before? One of my upperclassmen calls it the fishy. You just want to slam your head in the door. Do you mean the fishy? No, I don't mean the fishy. Okay. This is the proportionality symbol. If you see this means V is proportional to 1 over P. But since it's proportional to 1 over P, another way you could say that is V is inversely proportional to P. We're going to start learning how this terminology works. Yep. That gets us about to our time limit for today. We'll pick up here on Wednesday. Fish, you're going to call it the fish.
Wow, this is a pervert law.